welcome back to another video where we want to quickly take a look how you can define recurrent networks using the keras API. You will find a file which is called Bitcoin prediction in the colab folder under the lectures subfolder. And even though we name it Bitcoin prediction, actually there will no good predictions be made. So please only see this as an example how we can define a network including recurrent layers. Also, if you Google something like this, making big Bitcoin predictions using LSTMs, for instance, I think you will find plenty of blog entries. And in my experience, it sounds good, but often if you take a more narrow and deeper look at the models which are presented there, are not as succeeding as they are described there. So be careful. But there are some very good professional exceptions which are also provided by other researchers. Still, this is no promise for making with certainty the correct Bitcoin predictions, but I will show you in the end of the video some very interesting and, in my opinion, highly qualitative examples how you could set up, for instance, a Bitcoin prediction model. Okay, but for us at the moment, it's really about how can we define recurrent neural networks using the keras API. So first of all, take a look here. We are simply downloading the data, and we're using here the data of financialmodelingprep.com. And here we have a history of approximately 5 years. Here you can see what really happened to Bitcoin in the last years, and it's kind of, fascinating and, in my opinion, not really understandable what happened here, but that's how the world, or that's how the cookie crumbles. So what we are going to do, we will focus on not directly on the real prices, we focus on the differences from day to day. So because this looks like this is then stationary data, and is something or an attribute which is often quite good when it comes to modeling time series data. It's not really necessary here, and you can play around, and it kind of depend on the specific architecture of your model which you're using, if you're using rather non-stationary or stationary data. Anyway, it's not that important here. Important part here is that we will focus on the differences of the Bitcoin price day by day and try to predict it. We will try to predict it with its own history. In my example, will 5 days. So and so it really not is surprising to me this model is supposed to fail, because it usually takes more than just like the past observations in order to say something about the future. Okay, but here we'll use this simply as an example. So you can see here we have the adjusted closing prices, and here on the right we have then the first differences. So for instance, from the on November the 3rd, the Bitcoin dropped a little bit by about 52 US dollars, I guess here. I guess this is in dollars and not in Bitcoin or whatever, or in fiat, as you may call it, if you're in the crypto business. So here you can see then we have an increase, then it almost stays the same, and then we have another increase. So this is reflected by the relative or by the differences here. It's not the relative, it's just the first differences here. And what we will do is we use always 5 past observations in order to use it as like our sequence, which is processed with the recurrent unit, in order then to make a predictions regarding the next observation. So it's already very important, and here it starts for you to get important to take a look how we need to pre-process the data that such that it matches the requirements by recurrent units or recurrent networks. So what I'm doing here, and I think there are very likely more professional ways, but I think it quite serves here. So I want to always use the past 5 days, and we have a single feature variable here. So this is important for you. So we have only one feature variable, which is just simply the price difference itself. But we'll use 5 time steps, so the 5 past time steps. So a sample in our data set here looks like this, that we will have the 5 observations, previous prices, and the next day's price or the next day's difference in the price as the target variable. And then in the the next observation in our data set is more or less the same, with the exception that we move forward by 1 time step. So the previous target variable now becomes an explanatory variable, and the first observation from our first observation in the sample is dropped. What I mean here is, so 1, 2, 3, 4, 5 would be like what we'll use as the sequence for our single feature variable in the first step, and 6 at time step 6, this is our target observation. Then in the data set we move on. Now the 5 observations from our single feature variable are the observations on day 2, 3, 4, 5, 6. And the observation of our target variable is the observation of day 7, and so on and so on. And I generate so X is here are always like the 5 past observations at each time step, and Y is then like the current or the next day. So if we do it like this, and we can take a look. So take a look here. So let's do it here better. After doing this, for instance, if we take a look on our first example here in our sample, we have these observations, which are the sequence of 5 days of our single feature variable past Bitcoin price differences. And the target observation here is this value. Okay, and now take a look in our data set or the relevant data which is used for it. And if we take a look at the first observations here, you can see this. So we have here the first 5 observations in the data set, and then this is our for our target prediction. Now in our data set as I constructed it here for our model, now and the second sample of our data set is then 5 values starting here, and this one here gets our new target variable, which you can see here if you take a look. So this is that value. Okay, so I hope that makes it clear. So because the really important part when it comes to defining a recurrent network or a recurrent layer using the keras API is to provide data in the correct shape here. Okay, so and we'll talk about it in a minute, but first of all, you really need to understand we always have sequences now for our feature variables and not single realizations of our feature variable. So assume, for instance, for the moment, you would not only use its past own values, but also, for instance, use the volume here. Then we would need to construct here the data in a way that we have 5 observations of its own price changes and 5 observations of the volume. So then we would have 5 time steps. So we would have a sequence of 5 time steps, but 2 feature variables. Okay, so this is a further dimension which needs to be taken into account when we are using recurrent networks, because for forward neural networks we only have a single dimension, which is the number of feature variables. Here we have a second dimension, it's the number of feature variables and the time steps we are using for each sample in our data set. Really important, and if you understand this, doesn't mean you have to understand it right now, but once you understood this, it really will be more clear to you what recurrent networks are and what recurrent layers are, okay? And this is, so then I do basically something which you are already used to. So I split the data here, not really in a sophisticated way. I only use just like the first 70% we use for training and the remaining 30% of the data we use for testing. I use standard scaling. I use two scalars here, so I really divide here between feature variables and target variable. But this is, I don't know if really everyone agrees if this is the best way how it's done, but I think it is really reasonable and makes sense. So that's why I'm doing it in this way. And then, so once we have done this, the really important part is here, keras needs this form of shape for recurrent data. So the first dimension here is something you may want to ignore, but this is just the amount of data we have, so the batch size. But then it needs the data shaped in a way that we have the time dimension here and the feature dimension here. Okay, so that means if you take a look here, if we use xtrain and now, so the first sample from the batch is given here. Now the second dimension is like that we have 5 values here, and the other dimension is the amount of feature variables. So again, if we would have used also the volume as an additional feature variable, the shape of the first batch would be 5 times 2. That's important just because that's how it is defined using the keras API. Okay, so it needs first the time steps as an information and then the amount of feature variables. So that's really important. Always this is what happens over time, and this is how many variables we have which insert information at each time step. Okay, again, doesn't need to make sense right now, but once you've understood this, you really make a big step, in my opinion, in understanding how recurrent networks are defined and what they are doing. Okay, and now everything gets quite easy, in my opinion, because it works very similar to the way that we already have done it for forward neural networks. Again, we can use the sequential method here in order to define the recurrent model. So what I always like to do is first in a separate step define the input dimension. And again, I'm highlighting it here. For the forward neural network, we simply needed to tell the model here the amount of feature variables. For recurrent networks or recurrent layers, which follow after the input, we need to provide two information or two different informational sources here. The first one is how many time steps do we have per sample in our data set, and how many features do we have per time step and per sample. And with this information, keras needs now knows how to process the data through the recurrent neural network layer. Here we have a simple recurrent neural network. This is how you have, this is more or less the version that you've been told in the lectures. And but you could now, if you understand this, you could also replace a simple recurrent network, for instance, with a GRU, which is the gated recurrent unit, or you can write here the LSTM, which would be the long short-term memory unit. So even you do not understand it right now, you could easily reuse it, which is something which I do not recommend, but it's possible. Okay, so, but let's keep it with the simple RNN. So really the only difference to before when we had forward neural networks is that we need to shape the data, which is different than before because we have now an additional time dimension. But then once we've handed this information over to the model by the input layer, then we can say, hey, now please process the data as you know it per definition of a simple recurrent unit. 5 is the number of hidden units here, so we're generating 5 times, or we're doing 5 times the thing that I've been that I told you in our easy example. But obviously we're doing in one step, so using just a matrix of parameters. But here are 5 hidden states are generated at each time step. And if you would write 50, then 50 hidden states would be generated at each time step. Now I'm using a dropout here, which is always something that may prevent it from overfitting. I already did this here because it kind of helps here to at least make sure that also the losses during training also fall for the test data. And then what I'm doing here is to add a a fully connected layer on top of the output of the recurrent network. So yeah, let me just show, how can I show you this? After the model is defined, you can use the summary method, and it shows you in which form data is given by each layer. So for instance here, you see that after the information of the data is processed through the simple recurrent layer, then you have, for each sample in your data set, you have 5 values, so the final hidden states of the recurrent layer. If you, for instance, would have a return sequences equal to true here, that means you now will use a sequence to sequence model. Then you will see that after this layer, you will have, for each observation in your data set, you will have 5 time steps of 5 hidden state observations. Okay, but this is something we do not really need here in our case, so that's why I'm deleting this again. So after the recurrent layer, you will have for each observation 5 hidden states at the final time step t. And then as you know it from like these 5 values will be treated as you know it from a common forward neural network layer if you add a simply fully connected dense layer on top here. So each of these 5 values will be weighted with a parameter, and then adding a bias parameter will lead to an affine transformation function, which results in a single variable value here. Okay, and this is what we will use as a prediction for the target value here. Okay, I know really in the beginning this all can be very confusing, but the more often you hear stuff like that, the more you work with it by yourself, the more easy it will get and the better you will understand this. Okay, and the rest is really as you know it already. So we have a regression task here. That's why we're using the mean squared error when compiling the model. I don't know why by default always use the ADAM optimizer, and then we fit the model, we use the training data, we use the test data directly, which is also going to be evaluated during training, and we train the model for 30 epochs here. And as you can see here, something is learned here. Okay, so that's how the loss of the training data and of the test data both get smaller during training, even though it isn't that much. But then just to get an impression how well the predictions work, I like to use the actual realizations and compare them to the actual predictions. So that's why I'm using the inverse transformation of the scaling above here. And in the best setting, your model should result in something in like all these points here are the comparison of the prediction with the actual realization. So for instance, here we have a prediction of -50, but the actual realization is 1,000 or almost 1,000. And in a very good model, there should be at least a high correlation, a high positive correlation here. And in the perfect model would result in points which are only in the diagonal line here. Okay, as you can see here, this doesn't really work quite well, and yeah, there are big deviations, and so as the model as it is, I would really highly not recommend to use it. But as I said before, this is really not the focus here or the aim here. The focus here is that you see 2 things. First of all, you need to reshape the data such that the model understands that you now have for each sample in your data set, you have a sequence of realizations of a certain amount of feature errors. And then you can work with the model and the model definitions as you are used to it. Okay. Good. So, but if you're really planning on setting up a Bitcoin prediction model, then you should really do work harder here. So for instance, you could start by trying different feature errors, maybe reformulate the problem, not use the first differences, maybe just redefine it as a classification problem by making predictions in up or downward movements. You may try different model architectures, and you may get more data because here we only have about a little bit more than 1,000 data points for training a model, which in my experience is quite, not really much. But as I said, most important part is really here, take a look at the reshape and see that it is kind of easy to define the model and work with it. Nevertheless, if you want to dig deeper here, what I would highly recommend you, I would recommend you to search for this book here, so Machine Learning in Finance, From Theory to Practice by Matthew Dixon and 2 other authors, which is, I think, Igor Halperin and, let me take a look, Paul Billercon. I hope I'm spelling that right. But if you are, logged in to the Passauer Suchportal, just search for it. You can go on full text here, then it will directly lead you to this site, and here you can download the book PDF. And in the book, in the 8th chapter, and at the end of the 8th chapter, for instance, you will find here a Bitcoin prediction example. And the very nice part here is that with these examples in the book, they are based on programmed examples, which are available also to people from the outside. So you can find it in the GitHub repository of Matthew Dixon. So if you are just searching for Machine Learning in Finance GitHub, then take a look for the name of Dixon, so MFR Dixon here, at least during the time of recording. That's how it's called here. And if you click on that and go to chapter 8, you will find here a Machine Learning in Finance RNNs Bitcoin notebook. And you can download it, or you can just read through it here. And here you will find many interesting explanations and a very well written code, which can be used to make Bitcoin predictions, which are obviously better than in my example. So just take a look. I really can recommend the book here. It's a very nice book. It's a little bit too detailed in comparison to what we are doing in the course. So that's not really a disadvantage of the book, it's rather a disadvantage of the course. But in the course, I need to, I need to keep it more simple and narrow it down a little bit, because we do not have enough time to really discuss all this in detail. But in this book, it really discusses, I really like especially the advanced neural network chapter, because it relates the recurrent neural networks to traditional time series modeling, and it really shows some nice examples where we can use it. And one of these nice examples is given here in the end, so the Bitcoin prediction example, and also another very interesting examples like predicting up and downward movements, so upticks and downticks from a limit order book, which is really very granular stock price data. So as I said, I would really recommend it to you. It's not mandatory for this course, obviously, that you really need to know this, and yet you are going that much into detail here. We are focusing more on the broader picture here, but as I said, if you're looking for a more sophisticated code example on how predicting Bitcoin prices, I definitely can recommend this. And please do not let other people fool you, promising you very accurate Bitcoin predictions in certain blog entries, because sometimes it's not really good, to be honest. Okay, so anyway, I hope this helps, and see you in the next video, where we're going to discuss convolutional neural networks. Bye bye.